Welcome to video 5. Video 5 is alive. I've always wanted to say that. Great movie. Okay, so video 5. What have we learned in video 4? We learned in video 4 that the configuration of the partnered output coils will starve the input coil off, and the input coil is not able to get the voltage up on the partnered output coils as a result. Now we know that we need voltage because the current is equal to V over R. Current I equals V over R, Ohm's law. So we know we need the voltage up. So we need to find a method of getting the voltage up, which means that the partnered output coils need to be set up in a way that it doesn't stop the input coil doing what it needs to do on that particular phase of the cycle. Okay, the first and the easiest way to actually achieve this is through what we call delayed conduction. Okay, now delayed conduction is a method of delaying the conduction of one of these coils until a certain voltage has been reached. When a certain voltage has been reached, then the conduction of those coils will then kick in, and at that stage then the coils become partnered output coils. Now the kicking in of the partnered output coils can actually help increase the voltage, because one of these coils will slap, if you like. Now I tend to think of the magnetic fields as ocean waves, and I've shown a video several times of an ocean wave. A lovely lady has taken a video. It's one of the best I've seen of two ocean waves slapping together.
Nature is so dramatic, isn't it? Very dramatic. Wow. Wow. Like symphony.
And creating a very high amplitude. So you do need to be careful. There's a disclaimer on my website. Please go and read it. And look, honestly, I just want to say to everyone, be careful, because it can be dangerous. Watch your equipment and all that sort of thing. Okay, we cannot be held responsible, obviously, for experiments that you decide to do that damages equipment. Okay, this is something that I have warned you, and we've done the best we can, and that's all we can do. Anyway, moving on. When the coils conduct in such a fashion as to slap the coils together, one of the coils will conduct with the other one at a very fast rate, and the change in time, again, you've got to remember, time, rise over run, same as the last video, change in time between the two coils can actually increase the voltage even further. So the input coil may not necessarily determine the exact voltage on the output coils. The exact voltage on the output coils would more so be determined by the change in time of these two coils. It's configuration dependent. We have obviously like I say, the change in time is dependent here. All systems will be different. This is very hard to predict, very hard to estimate, and it's fiddly. It's a bit hard to actually achieve this goal. In video 5, I hope to be able to show you at least part of what we're trying to explain here, but what I also want to do is direct you to our website. There is a thread there, important delayed conduction in bucking coils. Okay, the thread's been there for quite some time, and I'll show you that now. Okay, so this is the important delayed conduction in bucking coils. This is a really important thread. Some of the members on the aboveunity.com already know that. Go going through this thread explains the importance of delaying the conduction on the output coils. So if we were to say this is the load, this is our basic circuit, load down here, okay, we have load up there. This is partnered output coil 1, partnered output coil 2. What we're doing here is we're giving people the idea of switching these coils in at a certain time. Okay, that time is when this particular terminal here becomes 18 volts or more. Now this is a pseudo circuit. This circuit is not meant to work. What it's meant to do is give people the idea of switching the coils in at a particular time. Okay, we are switching, we're conducting as the thread says, so we're conducting in the bucking coils at a particular time, and the time is delayed. Okay. Now the very fact that these coils do switch in, and the very fact that these coils have a voltage on them, and remembering that the change in current on the primary coil creates a voltage on the secondary coil, and the fact that a voltage can exist without a current is something that's very important that people need to keep in the back of their head. We can have a voltage here of whatever volts we want, but have no conduction. Okay, it's basically like a power supply. If we would imagine that this is a great big set of batteries stored away in a shed somewhere. Okay, we've got a terminal coming out, and the terminal coming out can can provide us with a voltage of 18 volts. Okay, that 18 volts is there regardless of whether we connect a load to it or not. Okay, there is 18 volts on that terminal as long as the batteries are able to give us 18 volts. Okay, remember 18 volts is a difference between this terminal here and in this case would be this terminal up here. Okay, that coil is a battery bank. Each side of the coil is a terminal, and it's a difference in polarity. Okay, so this circuit is a pseudo circuit, not meant to be implemented, but meant to give you the idea of switching in the coils at a particular time. And that time being 18 volts once that terminal has reached that 18 volts. Remembering we're changing magnetic fields in time, so the change in time will give us a delay, and the delay will depend on how quickly this coil is able to come up to 18 volts or more. Alright, now this is another instance. The MEG team said about a TVS. A TVS is a transient voltage suppressor. Say for example we had a line coming in from the road, wherever it's coming in from. Now that's a bit of an extreme situation. Obviously this would be some sort of circuit protection rather than a line protection. But anyway, to give you the idea, we've got a line coming in. For some reason we have a spike that's generated somewhere out here. Say for example someone's over here starting up their hairdryer or something like that. It's a very sensitive circuit. We need the circuit trimmed off at exactly 5 volts. Anything more than 5 volts is no good for our circuit. The circuit will blow if we have anything more than 5 volts. Very sensitive circuit. The TVS is rated at 5 volts, which is hard to get to, by the way. TVS is normally rated at higher or a strange voltage, 14.5 volts or whatever. So look around, do your research on it. But as the line comes in, as the spike comes in on the positive rail here, our TVS will see a peak, okay, that's much greater than a 5 volts, and because it's this particular one, this imaginary one here, is rated at 5 volts, it's going to dump anything above 5 volts straight to ground. Okay, so it becomes a dead short in the circuit across the TVS after that particular voltage. So you could say a TVS is a voltage controlled switch. Okay, anything over a certain voltage, it clips it. It's a clamped system. Okay, so it clamps the voltage. Just on this, I just want to say that I replicated the MEG back in the early days. My first 17th the 6th 09. I went through, I wrote to the MEG team, got permission to do a public replication. Started off pretty well, but I had a few problems. I made my initial MEG was just far too big, very hard to handle, very hard to lug around, and as any of you know that's worked with Met Glass before, little shards break off and they go everywhere. They get in your skin and it's sometimes very difficult to get them out, and they hurt like anything. Like normal splinters, but probably a little bit worse because they're sharper and they tend to go deeper, and there's more of them. Lots of little ones everywhere, and it's pretty painful. So anyway, I had problems with that. I got to a certain stage and then I shelved it. After that, I didn't publish anymore replications. I simply didn't publish any more after that because I got to the point where I built a small one and started sort of going a little bit off track over here. When I built the smaller one, which most of you have seen photos, when I built the smaller one, I got much better results out of it. It's much easier to manage, much easier to lug around and all that sort of thing. Anyway, I learnt about delayed conduction, the point of this, in and around these days, and I always wondered why. I always wondered what the significance of that was. And I just want to show you where I learnt of it and what I learnt, and the reason that I was actually focusing on that. Okay, this is the JLN website. Most of you are all familiar with this. JLN's done a fantastic job with everything that he's done. Anyway, JLN website, tons and tons and tons of data. But if you do come down, here JLN has stated a very interesting, with flashing asterisks, a very interesting line. A conditioned R load, resistive load, 100 kilo ohms, non-inductive carbon 5 watts, or MOV, metal oxide varistor, is required for getting the output data as measured above. Now, why would JLN state such a sentence? It's a very profound sentence to say. First of all, he says required, and required is underlined and capitalized. So he's saying is required is you don't have any options. If you don't do this, you will not be able to achieve the output. Okay, MOV is basically a switching device which is controlled by the voltage again. Okay, so this is a very interesting statement to make. Now this over here, I actually kept up with some of this back in the day. Conditioned resistive load is we'll have a quick look, is that there. Carbon resistor, conditioned, and that's the resistive load, which is not the load that's actually being focused on. This is the conditioned resistive load on the other coil over here, other output coil. Now the MEG guys have two output coils, 1, 2. A conditioned resistive load is required, or MOV is required, over on this coil over here, is what JLN's saying. And what JLN's saying is, and was measuring, if you have a go back and have a look, he's measuring the output on this coil over here. So he's measuring this coil over here, the output on that. He's not measuring this coil over here. Doesn't measure that coil in any of the measurements or any of the data or anything that I've seen, at least anyway. I've not seen any measurements on this coil over here, on that one there. The MEG is a dual output coil. It's required. You can't get away from not doing it. I've tried to say it in the past. The MEG is just an instance of this device. Okay, so here JLN has given us a pot of gold, if you like. This is a very interesting, very important statement to make, and something that everybody needs to be very well aware of. An MOV is a voltage controlled switch. We might go back quickly, have a bit more of a look. Okay, so these are the basic circuit schematics for, that's a bidirectional TVS, unidirectional TVS, Zener diode, very similar sort of thing, metal oxide resistor, MOV, and look, see it's got the, after a certain voltage there's a breakover voltage and then it conducts. Okay, this is the curve for a bidirectional TVS. Okay, so current here on this line. Okay, so at 0 voltage there's 0 current. Okay, as the voltage starts increasing, so does the current. Remember the rise over run? So this is a similar sort of thing. We're dealing with a similar sort of thing here, rise over run. Now the rise is the rise in current, while in this case the run is voltage. Okay, before we saw the run being time. Okay, in this case we're looking at voltage. Alright, so bidirectional TVS, this is the curve. Over here is considered VCL, VC is considered conduction. It's when the TVS has basically been considered as conducting. Okay, and current will flow, obviously, because we're above the line. And at that particular point in time, the current will depend on the voltage as current through the TVS. Now there will be a small resistance in the TVS. All devices have resistance of some kind, or capacitance, or resistance, or whatever. And that needs to be realized, so we just sort of take that for granted sometimes. Now this is the MOV, which JLN referenced. Okay, and this is a similar sort of thing. So over time we might have a voltage that might get up to say 250 volts in this case, and then once we hit 250 volts then the MOV will conduct, in this case 1 milliampere, and the conduction will keep going up as we go up in voltage. So once we start conducting there's an avalanche, and the avalanche will all of a sudden conduct. Okay, and we're looking at conduction. Once it's started conducting and the avalanche has been hit, then it conducts, and the current will be dependent on the voltage, so V over I and all that sort of stuff. V over R equals I and all that sort of stuff. Okay, so MOV or varistor is a voltage controlled switch, the same as a TVS is. Okay, and we saw, okay, JLN is saying it's required, we need something along these lines to make sure that in this case our little switch here on this coil is switching in. Okay, so the switch is switching in when this coil reaches a certain voltage. And isn't that a profound statement? Because what we're saying here is when our input coils have managed to get our voltage up in our coils, which was the problem that we saw in video 4, once our voltage is up, our coils conduct here, because of the switch here, we have a certain voltage applied across this voltage controlled switch, which might be a TVS or a MOV or a varistor or something similar, or even a special little circuit that's set up. Once that voltage is reached, then our coils conduct and slap together. Okay, current will flow, and that is the whole idea of the conduction. We conduct at a certain place, a certain point in time, when we have our voltages up. Okay, so effectively we've solved the situation by allowing our voltages to increase by delaying the conduction. The reason I am showing coils like this is to try and get people's mind away from the bifilar coil analogy. People keep talking about bifilar coils. Now what we're seeing here is we're seeing half a bifilar coil. This half of the coil up here is bifilar by its very definition. Bifilar is a term I've sort of said before that I don't like. We've got parallel wires around the length of, in this case it's only half the length of the former. I want to show here, we have a situation if you were to trace these circuits effectively are, and again, I've always said it, measure your currents, look at your currents. Your currents are what's important. Okay, your currents are so important, it's just not funny. You have to have 180-degree currents. Okay, your currents have to be out of phase. If your currents are not out of phase, then this will never work. You just got a transformer, and we all know a transformer is a symmetrical machine, equal and opposite, less losses. Okay, they should rename a transformer equal and opposite, less losses. Okay, long, horrible, yucky name, but let's be straight up and honest. A transformer is designed to be under unity. Okay, never ever will go over unity. Anyway, back to the point. If we were to trace the currents, okay, TVS up here, diode here. Diodes I've put in twofold. First of all, to give you an idea of which way the currents are traveling up through the bottom of the coil. Okay, out of this coil we've got a diode which is blocking it. Okay, so if we were to follow the these two terminals up, if we follow these two terminals up, then these two terminals, if the currents were moving in the same direction, then we'd have something that would be not equal and opposite. Okay, so this is opposite, this is blocking. Okay, so we're blocking with this diode. We're saying to this particular piece of the coil here, no, you're not having current come up this way. Okay, we can only have current go down that way. This one here is the opposite. We've got the diode on the opposite leg. Current can only come up this way. Okay, can't come back this way because the diode blocks. Okay, so what we are doing here is we're saying, okay, we're only allowing this circuit to achieve a state where the currents can only be equal and opposite. Now, for the sake of argument, I have a 50% duty cycle in here. Okay, and you can probably hear, if you listen close, you can probably hear a bit of a yucky noise in there. Okay, again measuring the currents. Yucky noise is all that on the scope. Okay, what I've done is I've tuned my input into the switch to only just trigger. We're just triggering. Okay, and we're getting all sorts of yucky noise in there. But if we zoom in, bringing the currents down, you will see we do in fact have currents that are not exactly equal and opposite, but they're pretty close. Okay, we have an effect in there where the effect is showing equal and opposite currents. We do have a primary coil that's injecting a signal into the core here. These two coils, this coil here and this coil here, are equal and opposite. We're powering a load. If we can focus in on that. Okay, that's a bit better. We have a bit better of a focus. Okay, so we have power, we have current in the circuit, which this phone would automatically adjust its focus. Anyway, okay, so we have a circuit that is running. The delayed conduction is via this TVS here. Okay, we've got tons and tons of noise in the core. Okay, the core's going, yeah, I don't sort of really like this. This is awfully terrible. And we can see that if we zoom out, we do get lots of noise. It's very noisy. Realistically, you really don't want this. This is, again, this is something that we don't really want. Now, if I were to play with the input signal and turn the input signal up a bit, we'd lose some of this. And there you go. You can probably hear in the background the noise has stopped. We've still got lots of noise though. We've still got lots of noise in the trace. And again, this is not ideal. We really don't want this. Okay, we zoom right out. There's our 50% duty cycle. And what can we see? If we were to say, okay, well, what have we actually got here? You can see we've got a switch here, a switch here, a switch here, and a switch here. So in our 50% duty cycle, we've got a on period of, well, what is our frequency? Our frequency is roughly according to our function generator, we've got a frequency of roughly about just under 11 kilohertz. Now you've got to remember this circuit is what we're seeing here. If we were to zoom in even a little bit more, what we're seeing here is we're seeing delayed switches, all these little peaks or little sharp bits here. This is where the delayed switch is, and remember this is the current. So what we're seeing is we're seeing the TVS switch in at different stages here. So as soon as we get the TVS voltage, okay, climbs up, and the current. Remember on the TVS curve we have a x-axis this way, y-axis this way, and we have a curve that's sort of like that. So when there's 0 voltage, there's 0 current, and then the current will slowly increase, and then all of a sudden it will switch. Well, that's what we're seeing here. So we're seeing the current ramp up a little bit, it slowly increases, and then all of a sudden we're seeing conduction. This is TVS conduction over here. And if we zoom out, you can see we've got all these little, and they're funny, they're odd. Zoom out a bit more. So we've got these equal and opposite switches where the current is conducting. Very, very short in time. We're 100 nanoseconds here, and we're even less than 100 nanoseconds from there to there. So what we're seeing really is not an optimal setup. This setup is not optimal. You can see we've got a little bit more light now. I always love to see, you can see just on the screen there is a bit of that blue light. You can see the edges come off. You get a bit of blue light on the right angle. You can tell that the energy coming off the light is not the same as just a basic DC current. It's a little bit different. Alright, so what are we sort of learning here? What are we learning? We're learning that yes, we've got equal and opposite currents in the coils. Yes, our input is triggering these coils to do what we want it to do. Yes, we have found we've found a position, if you like, or we've found a frequency, we've found a tuning that does seem to work. And at this stage we don't have a machine that's above unity. It's definitely under unity at the moment, even though we have the right effects. So we've got to ask the question, why don't we have a machine that's above unity? Okay, remember, unity is a combination or the summation of the voltage and the current. Okay, and what we've got is we've got a voltage and a current that is not sufficient to be able to move the machine into a state where it's going to go above unity. Okay, our voltage is not high enough, therefore our current won't be able to flow in a timely manner. And remember, we get the voltage goes up, and then we conduct on our TVS, which is over here, and then as the TVS conducts, we then have a period of time where the voltage will reduce. So in other words, the conduction, the slapping together of the waves, which essentially is this peak here. Okay, and we do see a little bit of decay there, but we're way off. Okay, what we're doing is we're getting up here, two coils are equal and opposite. Okay, so there is a fight going on, but the fight is not right. We need to do some more work. There's a lot more tuning, there's a lot more fiddling that we need to do. And I think at this stage what we need to do is we need to look at the placement of our coils. Now, every time you see waves on the beach, okay, you might see a wave, it'll come rushing up the beach, and you see all that volume of water up on the beach, and then all of a sudden all that volume of water comes rushing down the beach again. Almost just as fast as it went up the beach, it's moving down the beach at the same speed. All that volume of water, and all that volume of water can hit the opposite volume of water coming back down the other way. Okay, so we have effectively two volumes of water, and the two volumes of water are hitting each other, both at different speeds. We have different speeds, okay, because the water coming down the beach is slower, generally a little bit slower than what the water does rush up on the beach. So as the water rushes up on the beach, the volume of water rushing up on the beach is normally a little bit quicker, if you have a look and study it, than what the water is rushing down the beach again. Okay, so we have a point where the waves themselves meet, and that point is where the overall volumes of each waves are equal and opposite at the same time. If you stop and sort of think about that statement, that's a very profound statement, because that means that the magnetic fields, if you were to think of each magnetic field as a whole from each coil, that means that the position of the coils, it means the distance where they are in the core. So if one was here and one was here, and you were to look at the magnetic fields between the two coils, then over here and over here would be where your biggest standing waves would occur. Okay, so the magnetic fields would rush around this way, magnetic field would rush around this way, they would meet each other about here, and there'd be a standing wave, which the wave fronts, the front of the wave would meet at the middle, but would build as in time. Okay, remember this is a time weighted average, so the magnetic fields would meet in the middle and would get stronger and stronger and stronger as the current ramps up in the coil. As they meet, the currents would increase in each coil, so the current, remember the current ramps, we looked at that in the last video. Okay, so the current ramps between each coil from here to here, and the magnetic field would meet over here, but would propagate all the way through the entire length of the core, both sides. Okay, now you got to remember there's actually 4 waves that are doing work here. Okay, there's always an equal and opposite, and every time we have one coil, for each coil there's an equal and opposite. Okay, so there's a first wave that comes round. This coil over here has a first wave that comes round, and because of the change in this coil over here, the magnetic field in this coil over here would induce an equal and opposite in this coil over here, but at the same time this coil over here, the change in this coil, change in current, would induce an equal and opposite over here. Okay, so there's 4 waves all going on, all interacting all at the same time in the core. Okay, we've got to think about where the cores are placed. Okay, and remember Floyd Sweet talked about a signal propagating through space. Okay, and he talked about the time component. Okay, so what is the time component? If we're counting seconds, 1, 2, 3, all that sort of thing, what's the delay, what's the propagation delay for each magnetic field to do what it needs to do? Okay, when the coils are wound on top of each other, we can see the propagation delay is very, 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 very small, 100 nanoseconds. Okay, now if you look at the Tarell-Capanazzi device, they say that the spike, that the nanosecond, they call it the GSN, I think it is, short for nanosecond pulsar. The nanosecond pulsar has to be in 5 microseconds. And why does it have to be so short? Is because the propagation delay of the waves, and remember we're talking about a quarter wave here, so it has to have a pulse that gets the voltage up to here and then instantly switch off within this time frame. The propagation delay in here, okay, or in here, so if you wanted to go from here to here, so half 100 nanoseconds there, and we're looking at 50 nanoseconds, and we need a propagation delay within that 50 nanoseconds that can get the voltage up, and it has to be resonant. So we are learning a lot we're at a stage now where we have a huge amount of data. Okay, a few simple experiments on the bench. We've proved that yes, we can get equal and opposite waveforms, which is not very hard. It doesn't take long on the bench. And again, if you go back to what we were talking about before, we have always talked about measure your currents. Your currents tell you what's going on. Okay, and then the right hand grip rule. Okay, if we were to say, okay, well, we know that the current in this coil is going that way. Okay, we know that it comes in this cable over here, and we know that cable is wrapped that way. Okay, so that is going to create a magnetic field that goes that way. So we're going to have a north pole at this end over here. Okay, if you follow this one, the diode here, okay, it comes in this way. Now, if you follow the current in from there and use the right hand grip rule, then we have a magnetic field that way. Okay, now I've shown all along the magnetic fields have to be equal and opposite. So we have a north pole up this way on one of the coils, on this coil over here, and we have a north pole up this way on this coil over here. So we have equal and opposite magnetic fields. Magnetic fields are equal and opposite between the two coils, and there's the proof there. Okay, the proof currently tells us that we don't have enough voltage, and our coil configurations are not right, not sufficient to be able to produce large enough voltage and current output, for the simple reason is the propagation delay is too fast and we're not able to catch it. Okay, a frequency needs to be up around several tens of megahertz to be able to get into there. Okay, and that is really too fast. It's, for some people, it's sort of out of range. Now, that doesn't mean that you can't have a machine that doesn't run at 50 hertz or something along those lines, or 60 hertz or something. It just means that to catch that wave and to make that wave do work for you, you need something in there that's very, very, very fast. Okay, it's sort of something that's really too fast for most people. Most people, to do a little bit of work on the bench, it's just too fast for most people. Okay, so I think this video is long enough. We've learned a lot out of this video. We have achieved a goal. Okay, the goal is to get magnetic fields that are equal and opposite between the two coils. We have, again, a 50% duty cycle on the input coil at just under 11 kilohertz. Okay, and that's just a frequency that I've sort of tuned to get a reasonable wave on the output, so I can sort of show you what's going on. Now, this doesn't mean that this is the optimal frequency for this device. If someone were to play with it, reduce the duty cycle right down, look for a better duty cycle and frequency, because remembering a very short pulse on the input is what we need at a particular frequency. Just to explain that, if we have a very short pulse, okay, if we have a very short pulse, remembering we've got to get our voltage up. So once our voltage is up, then we hold the connection, we hold the conduction on the coils. Now that would mean at this stage, once we've conducted, which would be at the peak, we hold the conduction, but the input would be off. So the input is off, and then we let our coils just reduce down to 0. So that's why we need a frequency. So the frequency determines our off time in combination with the duty cycle. So duty cycle might be 10%. We have a 10% pulse in here, which is 10% of the frequency. Okay, frequency between the two fingers. 10% of that frequency would be, there'd be an on time, and then off time, and the rest of the off time would be conduction, which lets our, you can sort of see it there, but it's not right. You can sort of see that there's a drop, there's a decay, and you can see that decay is very much slower than what the initial increase in amplitude is. So if we were to go from here to peak, the time that it takes on the x-axis moving this way the time it takes is very much shorter than what it takes to go from here to the trough, okay, to the lowest possible amplitude. Alright, I think this video is long enough. I hope we've learnt something. We certainly are a lot further ahead. We understand the coils a lot better than what we did initially. Our experiments are a lot further ahead. Now what we've got to do is we've got to think about how we can improve the device, how we can make this machine better. We've got to think about our magnetic fields, and remembering just like an antenna, the magnetic fields from the coils propagate through space. So we have the current in the coil, which if you use the right hand grip rule, remembering before we were sort of doing this, the right hand grip rule, we've got a current that's telling us that we've got a north pole up here, but the north pole, they always enclose on themselves, so there's always a magnetic field that encloses on themselves. So the current might be moving that way, but the magnetic field is moving that way. There's always a 90-degree from the current to the magnetic field, and we'll show you that now. So the whole idea of this is that when there is a magnetic field, it takes time for the magnetic field to propagate through this core. So again, if we were to put a coil up here, okay, if we pulse the coil from over here, we could measure a time delay that it takes for this coil over here to see the same equal and opposite current. Okay, and you can sort of see that here. So if we were to, and if we zoom in maybe a little bit. Okay, so what I'm sort of trying to show here is the peak of this yellow wave up here and the peak of the red wave down here. There is a time delay already that you can see. Now that's in the nanoseconds, so if we were to even move it out a little bit more, I'll just freeze it there for a second. So we can say roughly the peak on the yellow is about here. We're down to 10 nanoseconds, and the peak of the red one is about here. So we're only several nanoseconds in time. The peaks, the difference between the peaks is only several nanoseconds in time. Okay, and that's just between these two coils here. Now you've got to remember at the same time there is a delay in the discretes. So our diodes, TVS and diodes here, there will be a difference in delay between those. You've got to take that into account. Take into account the wire length difference, all that sort of thing. Take into account there might be a 0.1% difference between that resistor, and so on and so forth. There's lots of things that you've got to sort of take into account. So those sorts of things you've got to take into account. You've got to realise that yes, there will be a delay, a propagation delay in the magnetic fields. Okay, what you can see as a wave here, okay, what you can see as a wave here, and remembering this is the current, so what you can see as a wave here has got to be thought about as a wave over here. Okay, remembering that your magnetic fields are just exactly the same kind of wave that we use in antennas. It's the same thing, the exact same thing. There's no difference. Okay, the current, the voltage, the magnetic field, the propagation delay through space, the whole lot, everything is different. And I suggest go and read Floyd Sweet's paper, Nothing is Something, and particularly focus on, at this stage, the time delay that Floyd Sweet talks about. When a signal propagates through space, it can be lost with reference to a single point at a particular time. Okay, so remembering that this is something that when Floyd Sweet talked about that this is what we're dealing with, is the propagation delay through space, and we've got to count the core as space. Okay, the core will be different. All cores are different. That's part of the reason why we can't predict these devices. Very hard. Cores are different. coils are different, inductances all will be different, diodes will be different, different means of switching, all that sort of thing. Everything will be different, so very hard to predict. But what I'm trying to show in these series of videos is the methods and steps of learning how to progress with bucking coils to get what we want, to get a machine that produces sufficient energy. And remembering, we're pumping the energy from where the energy is. We're not generating it. There's no such thing as generating energy. Energy is, it's there, okay? It's the charge in the coils and conductors everywhere. The electrons and neutrons, neutrons have no charge, sorry, electrons, protons, ions, the holes where the electrons leave. So the copper coil itself is full of charge, and electrons come in from all sorts of places. You know, it can be sucked up from the earth. That's why sometimes some of these devices need an earth, so they can be sucked up from earth and various other different places as well. I don't really want to move into a debate about that, but there's enough charge in that wire to run a small city for a month or so. Okay, this is long enough. I just want to shout out to all our members. We've got a fantastic team of members. Really want to thank them. Without them, this would not be possible. For those that are following that can afford it, I'd like to ask, if this video has helped you, please consider a donation. Thank you everybody. I really appreciate everybody's effort. We are changing history. What we have done already is we've changed every single forum's direction out there. If you visit any forum, they all look at the same technology as what we have been sharing for years now. Since at least 2011 is when I first started sharing bucking coils as a form of energy generation. This is hard. This is not an easy task. You know, we need several geniuses out there to come help and figure out the exact means. I'm trying to share everything I know, but we need several geniuses out there to come help us share the exact means how energy is generated, how to make these devices work, how to predict them. I have shared just about everything I know about these devices. I know that they work. We have proof. Okay, there's several machines out there on our forum. We have proof of running devices. It's just an understanding, and that's what this video series is about, to try and help people with their understanding, to try and help very small, very cheap experiments to move people forward in bucking coils. Partnered output coils do work. Okay, thank you again.